Hello everybody! Today I want to talk about self-organizing, distributed and learning technical systems. My name is Stefan Bosse, I'm a lecturer and researcher at the University of Bremen, and today I want to give an overview about a very interesting research topic and research field, self-organizing system, and towards technical self-star systems. What means self-star? Now, self-star is a set of capabilities and features of a relatively complex system and includes self-adaptation, self-organization, self-protection, self-awareness, self-communication, coordination, and so on, self-learning, and. So, self-star systems are very important, systems and system design that is used for future learning technical systems and to implement them and to make them robust. And this is not only limited to autonomic systems, to the features and capabilities of autonomic systems. There are software architectures, very important. That means distributed systems, multi-agent systems I will introduce here in this talk, modeling and simulation, performance engineering, and virtualization. On the other hand, this is one side, the software architecture. On the other hand, we have a major field of predictive data analytics or analysis. That means statistical modeling, machine learning, data-driven modeling, machine learning, time series forecast, critical event prediction, and so on. And of course, we have to do benchmarking and experimental analysis. That means to evaluate the performance, the energy efficiency, very important for distributed technical systems, security, dependability, and so on. And on one hand, experiments are used, real-world experiments or sandbox experiments. On the other hand, simulation is used as a method, as a technique. So, what are complex systems? Complex systems pose a behavior that is intrinsically unpredictable and uncontrollable, and that cannot be described in any complete or closed functional analytical manner. Complex systems can be composed of simple interacting cells. The components of a complex system are commonly called, in my terms of understanding, agents or cells of cellular automata. Cellular automata and agents are very similar. They have some common methodologies and architecture details that will be discussed later. So these are individual systems that act upon their environment in response to events they sense or experience. They interact with each other or the environment. This is a very important feature of such a complex system. So another very important feature is emergence. Simple interactions at the local level give rise to complex patterns at the global level with the aforementioned self-star capabilities. Here's an example we see. Here we see a cellular automata, the predecessor of multi-agent systems. Simplified multi-agent systems can be considered as cellular automata. And here you see an example from signal processing. Here we have a network of cells only connected to their neighbors. And the cells have only a very simple behavior. It's a very simple finite state machine. And here in this case, the cells have a state, and due to interaction with the neighborhood cells or the neighboring cells, the state changes. And the initial state was a frequency spectrum of an acoustic signal derived from a machine, from a technical device. And the goal is to find anomalies in the signal or anomalies in the operation of the machine. That means defects or something like that. And after some iterations of this very simple cellular automata, some specific patterns, here you see it, arise on the global level. We have the emergence. And some of these smaller patterns are candidates for anomalies. So this is a very simple example of emergence. So, self-organizing system. We can define them as a system where a collection of interacting elements give rise to the patterns of behavior that the individual elements are not capable of when they don't interact. So interaction leads to globally or more or less globally visible patterns of behavior. So a system which changes its basic structure as a function of its experience and environments, this is one of the main features of a self-organizing system. And this means we already introduced emergence and emergent properties. Organization can be defined as structure with function. The components, the agents of the systems are arranged in some kind of orderly way, a structure, so as to achieve a certain goal, a function. This cannot, in principle, not be controlled. Here, the patterns arising are not planned, not modeled. Only the local behavior of a cell and its interaction with its neighbor is modeled or programmed or designed. We hope that the emergent behavior, the global behavior, is the desired behavior. But anyway, self-organizing systems pose absence of external control, that means autonomy, decentralized control, dynamic operation, that means evolution over time, strongly related to the concept of agent-based systems, and resilience, failure of some elements do not affect system behavior. So resilience is a very important feature of self-organizing systems we want to achieve. So what are the self-organizing concepts? Self-organization can be considered as a problem of coordination and communication. So basically we have self-organization by alignment. That means the concept of division of labor that coordinates activities that happen simultaneously. That means in parallel. And the workflow is basically its complement. It coordinates activities that take place one after the other, sequentially. And finally, we have aggregation. This is shown here. The typically flow in coordination with different concepts. Here, the division of labor at the beginning. So we have parallelization and independent computation, communication. Then we have coordination on a more local level. And the workflow, coordination means basically sequentialization, sequential processing flows. And finally, we have again aggregation to get some system aggregates, some output aggregates, and the final product. So we distinguish strong and weak self-organizing systems. Strong self-organizing systems are those systems where there is no explicit central control, neither internally nor externally. And we have often weak self-organizing systems. And weak self-organizing systems pose, at least from an internal point of view, some kind of reorganization, maybe under an internal, central, or external control or planning. So, self-organization in technical and digital systems is mostly data-driven. And so we talk about knowledge. How can we derive knowledge from data and how can we understand data? What is the special and temporal context of data? So we distinguish deductive knowledge, inductive knowledge. Inductive knowledge is typically the case in data-driven methods like statistical modeling and machine learning. And information mapping, that means, for example, knowledge graphs that provide a bridge between deductive knowledge and inductive knowledge. But important is, machines do not have a priori access to deductive knowledge. So, here we have a lot of examples of self-organization in technical and digital systems that starts with dynamic communication structures, distributed sensor fusion, distributed crowd sensing, distributed learning and adaptivity, and finally distributed solving of optimization problems. Now, here we have the summary of fields of application of self-organization, self-organizing systems. Here I give some applications and use cases from my research over the past 10 years, 1 decade. And this starts with the already mentioned solving of distributed optimization or distributed solving of an optimization problem, and ends with data-driven agent-based surrogate modeling, combining agent-based methods with machine learning, and includes traffic flow optimization, decentralized, of course, with self-organization, distributed chatbot networks, mobile crowd sensing, human-in-the-loop simulation with mobile agents, distributed damage diagnostics, like structural health monitoring, and incremental distributed learning, for example, for seismic analysis. We have two main branches in my research and in the relevant areas of self-organizing systems and methods and research questions in self-organizing systems that are agents and data-driven modeling, that means machine learning. So I want to start with the agent methodology, that means multi-agent systems and the simpler predecessor cellular automata. And I distinguish in my work and in general agent-based modeling, agent-based simulation, agent-based computation, that means mobile and autonomous computational processes are agents, or agents are mobile and autonomous computational processes. Agent-supported and agent-based learning, including reinforcement learning, but not limited to. Then a combination, a hybrid, agent-based computation plus agent-based simulation and agent-based modeling. And finally, a hybrid of agents and cellular automatas, a more hierarchical system providing agents and cellular automatas or combining them. So let's start with the first use case, solving distributed optimization or distributed solving of an optimization problem. And the goal is self-organized optimization of a global mechanical property or of global mechanical properties. Here, for example, the minimization of the global strain energy of a mechanical structure. Of an adaptive robotic material structure only by local negotiation and adaptivity. This is the goal. The system is a network of physical and computational nodes connected by adaptive spring links. The technology here is not relevant, but we assume we have actuators that can change their stiffness, their damping capabilities, and so on. So each node is not only a cyber physical system, a physical node, it's an embedded computer too, with an agent processing platform. And this computer is connected to all its neighbor nodes. And connected to local strain displacement sensors and the already introduced actuators, changing stiffness damping between the mass nodes, the material nodes. And the algorithms addressed here in this work are multi-agent systems that perform, first of all, global optimization, decentralized, our global optimization, a segmented optimization, and the primary goal, local stiffness negotiation by controller agents on node level, on neighborhood level. This is shown here, a very complex image. Here the three algorithms in pseudocode notation. The algorithms itself are of similar program complexity, not computational complexity, program complexity. You see it here. They are very similar. The neighborhood algorithm, of course, is the most compacted algorithm, and bases only on a neighborhood interaction and by negotiation with neighborhood nodes. The segmented algorithms has a moving window to optimize segments, and the global algorithm just collects all the sensor data, computes new actuator values, and distributes the new actuator parameter variables. And here you see the typical structure, a adaptive robotic structure. Here the mass nodes connected via springs to the neighbor nodes, and here we have a whole. This is correct. Here we have the computer network. Here we have the physical network. They are overlaid, and a lot of agents are here processed on the specific agent processing nodes. And here we have a loading, and we have a hole, a defect, and so on. And the aim is to minimize, for example, the system aggregate global strain energy by modifying the stiffness of the actuators. Here are some results. very interestingly, if we do no optimization, we have the baseline. If we do global optimization, we are able to reduce the global strain energy by about 30%. The neighborhood algorithm, only performing with neighborhood negotiation, neighbor cell negotiation, can only provide a reduction of the, for example, total strain energy of about 10%, but in engineering 10% is relevant. It's not a very small number, it's relevant to reduce some kind of mechanical global properties. And but what is interesting too, in the first and the second algorithm case, the sum of all actuator stiffness that is related to the energy required to modify the actuators is increased here significantly. But in the case of the neighborhood negotiation algorithm, it's reduced. This is another important emergent behavior, but not desired in originally. It's just an outcome, an additional outcome that is very welcome, of course. Yeah. So here we have the two main global properties: total strain energy and total stiffness of all, sum of all the stiffness of all actuators. And in this algorithm, both are minimized. Minimized. And here we see the communication and computation cost, and of course the neighborhood algorithm is the winner and the global algorithm is the loser, of course. Yeah, the second use case, decentralized self-organized traffic flow optimization. The goal is traffic flow optimization, and that means minimization of the path length, the traveling path length, traveling time, and the reduction of jams with incremental long-range navigation learning in urban environments. The system consists of an artificial urban area with streets, crossing, traffic signs, vehicles, crowd flows, and interacting activity-based agents. And the algorithms are, again, self-organizing micro-level agents and micro-level vehicle navigation control using a combination of reinforcement learning and rule-based agents. And this hybrid approach is used to optimize route planning and decision-making in cities under varying local and global traffic simulations. Yeah, and agent-based modeling and simulation is used to study the emergence effects on urban city traffic flows. Here you see the hybrid architecture consisting of the rule state-based agent combined with reinforcement learning and a fusion module that finally drives the actuators. That means a vehicle driving left, right, forward, increasing speed, decreasing speed, and so on. And here you see the vehicle agents. They interact, for example, with traffic agents, traffic sign agents, with other vehicle agents, and so on. And the goal is global route optimization by local sensing and local decision making. And here you see some results. Over time, the agents learn, the vehicles learn, and the path efficiency, that means finding the shortest path, increases significantly over time. And the time efficiency, that means the shortest traveling time, this is not the same as the shortest path. This can be, for example, if you have jams, you can have the shortest path, but the longest traveling time. So this increases too by 20, 30% or 50%. And the path efficiency increases significantly. So reinforcement learning combined with an initial set of rules for navigation and route finding without any global maps, this is very important, is suitable to reduce the traveling path length and to reduce the traveling time. And of course, a fully decentralized self-organizing approach. The third use case is called human-in-the-loop simulation with mobile agents. That means we want to couple humans with agent-based simulation. Not in the sense of virtual reality or some kind of gaming. It's meant with the digital twin concept. That means we start with a synthetic simulation world with model parameters derived a priori from some kind of knowledge and so on, but with very limited variance. Then we couple humans to the simulation, and they should provide information that can be used to create digital twin agents in this simulation. And these digital twin agents provide more model variance based on the feedback of humans. And this is the goal is the fusion, already said, of simulation with real-world interaction and sensing to explain simulation-based aggregate effects or aggregated effects with enhanced model and data variance by the human interaction and the digital twin concept. So the system consists of the unified JavaScript agent machine attached to a two-dimensional world simulator, mobile devices, smartphones, processing the JAM Platform 2, mobile agents that bridging simulation and real-world environments. So they can migrate between the simulation world and the real world. So the algorithms are a combination of ABC, ABS, ABM, mobile crowd sensing, and digital twins. Here you see the basic, architecture, the basic methodology. Here, starting with a social model, for example, behavior model of crowds and so on, if we want to investigate segregation, for example, migration, and so on. So we have agent-based modeling, you can do agent-based simulation, we have an observation structure, of course, the emergence patterns we can observe, but then we add variance by agent-based simulation combined with crowd sensing. And the crowd sensing, the mobile crowd sensing, aims to create digital twins that are introduced in the simulation world. And we can observe structure, of course. We can observe no structure. That means the previously observed structures are destroyed, or we observe totally new structures. And here you see the basic concept. In both cases, JAM processing platform is used here for the simulation and for the real-world deployment in smartphone apps. And we have the same class of, or the same kind of agents that can be used here in simulation for simulating some kind of physical entity and for using it for distributed computing in this kind, mobile crowd sensing. So we have a very unified agent-based approach. Here you see some results. Here the synthetic simulation, here with a randomized initialization of peoples of two classes, A and B, blue and red. And due to, we're using here the Sakura social segregation model, and we have some model parameters, and if we choose some model parameters, we observe the already known and well observed in the real world, well observed segregation, rich people, poor people, black people, white people, whatever. Yeah, and but if we introduce digital twins by mobile crowd sensing, for example, performing a small, simple micro survey, so humans answer some questions about their living behavior, social interaction, and so on. And the return of these micro surveys are used to create new agents with a variant set, with variance in their parameter set. And then we observe, very interestingly, here some totally different patterns. First of all, the blue and red are closer together. The variant people, the variant digital twins in the simulation act as a glue to bring them together, and the clusters are bigger. So we have observed new and different structures just by introducing variance by mobile crowd sensing and the digital twin concept. Okay, this is now the second main area beside the agent-based approaches. We are now coming to data-driven modeling. But basically, in the sense of self-organizing system, I address in my research distributed machine learning. This is first of all the concept of multi-model machine learning with local inference and global fusion. That means global state estimation from local states. Then also with respect to self-start capabilities, self-adaptivity, incremental distributed machine learning. And finally, a combination or a hybrid or a fusion of agent-based methods with machine learning. So that is called surrogate modeling. Okay, here the first use case, distributed damage diagnostics, also called structural health monitoring. And the goal is robust detection of hidden damages in hybrid materials using guided ultrasonic waves and a distributed sensor network. This is part of my research group, or it's a project in my research group funded by the DFG. And the system consists of hybrid material plates. That means an alternate structure of metal and fiber laminates or fiber materials. And the material plates embeds or have applied sensors and actuators for guided ultrawave measurements. And there are two setups. Setup A, 12 with 12 discrete transducers, and B with one transducers and a special two-dimensional air ultrasonic scanning method, providing 250 by 250 virtual sensors. And output is always a time-dependent sensor signal. This is very important. The aim is to find hidden damages, and they can contain in their signal the damage feature. It's very hidden. Not only the damages are hidden, the damage feature in the signal is hidden too. And the algorithms that are used are multi-model instance ensemble learning and model fusion. And the global fusion is performed with different methods, negotiation, voting, point density clustering, center of mass methodologies, and so on. And the feature extraction is here commonly as a common discrete wavelet transformation. And the predictor is a state-based long short-term memory artificial neural network. So, but the basic concept is Holonomic principle, with the decomposition of large complex problems in multiple simple problems. That means applying the divide and conquer principle, and distributed local data processing. This is shown here. The original concept, we have a sensor network with distributed sensor data and sensors, and all the sensor data is collected to a central node, so a central computer, applied for the training of one data-driven model, a machine model. And we have one model with the global data and predicting a damage, for example. The new method with distributed machine learning means, and local prediction means, we have local models only operating on local sensor data, on one sensor data only from one sensor node. So we have a local model that is not very reliable, of course, but we have a lot of these models, and then we perform global fusion by some methods, and then we have a very robust global aggregate. That means a damage predictor. Not only there is a damage, there's no damage, the damage is of class ABC, we have special information. Where is the damage? So this is shown here. Here we have an artificial sensor network with data using from this ultrasonic air scanning method. Here an 8x8 network with 64 sensor nodes, and they use only their local time-dependent ultrasonic measuring signal data and perform a local prediction. Is there a damage in my neighborhood nearby? And here you see the X is the real damage, or a pseudo defect in this case. And here you see the activation of nodes. Here there are some nodes weakly activated. It's just noise or false positive, but it's really weak. So we have here very good case. So here these nodes are activated and say, yes, I assume in my neighborhood there's a damage. And then I can perform global fusion and say, okay, here the blue dot, here is the damage. With a very high accuracy, typically below the average sensor distance here, the special distance between sensors. Here we have another case with ambiguity, but after global fusion, I can still have a very accurate estimation of the damage position. Here the real and here the estimated. Here it's a much more problematic case with much more activations, wrong positive, false positive activations. We have no false negative activations. So we over all cases where there is no damage are recognized as no damage. That's very important. So the true negative rate is 100% in our approach. And here you see another very problematic case, but still the estimation of the damage position is relatively close to the real damage position. So this approach with local prediction and global fusion leads to a very robust, here for example, if we have node failures, we have still resilience, with a very high recognition of damages, a 100% true negative rate, and a position accuracy of about 1/2 of the sensor distance, just by the global fusion. But here we have a pre-trained system, and then we applied a trained model to new data. The second use case investigates incremental distributed learning. Here the use case is earthquake prediction using seismic data. The goal is robust detection of seismic events using a distributed sensor network, in this case the seismic sensor network itself, with incremental model updates and local prediction with global fusion. The system consists of the South California seismic network, or its data, mapped on a logical two-dimensional mesh grid, regular mesh grid, or ICT network, information communication technology network, with agent platforms, again JAM, and past seismic data of events from 20 years are used. So, and the algorithms are multi-agent systems, of course, and distributed incremental learning, but here using not an artificial neural network. Here we use a decision tree, a special decision tree learner and decision tree model based on confidence interval arithmetic. That means a sensor value gets a confidence interval, a noise interval, and so each sensor variable is related to a confidence interval, and the learner and the decision tree itself will use interval arithmetic to distinguish values. For example, the values 1 and 2 are different. 1 and 1.1 are different for a traditional decision tree learner. But with the confidence, the noise intervals, if they are relatively large, for example 0.5, then 1 and 2 are different, but 1 and 1.1 are not different. So they are treated as the same value. This is very important. And then we improved the algorithm, the interval arithmetic decision tree learner, by an incremental version. And you see the mapping of the South California seismic network on a regular mesh D network. It's just a logical network with neighborhood connectivity. And here the architecture or the flow in this incremental training with updates from new seismic events, improving the decision trees. Not simple to incremental train decision trees, but here you see some results. The black and blue are the results from the pre-trained interval decision tree learner, and we see accuracy an average about 80 to 90%, estimating the origin of the seismic event and to recognize the event, the strengths, and so on. It's an accumulated confidence value. But the interesting part is that the incremental learner that learns step by step, or with a pre-trained set but incremented or updated with new data sets, performs as well as the totally pre-trained version in most cases. And here you see, for example, a case where the incremental version has the same accuracy, the same confidence and prediction like the pre-trained monolithic trained version. So this was a very interesting result because the training of the updating of decision trees is critical, because a decision tree loses or discards information. But it was successful. So another example of a holonic system, holonic design principle. We have local prediction with global fusion, and the global fusion is the rescue for noise on the local level that suppress noise on the global level. And finally, data-driven agent-based surrogate modeling that is used to improve the accuracy of time series prediction of system observables by combining multi-agent systems with cellular automata simulation and with real-world data. Finally, performing surrogate modeling of aggregate variables. One example we investigated just in time, infection data, infection rates, an example of the COVID database. And to summarize, time series prediction on the data we are using from the Robert Koch Institute over 2 years approximately was not possible. The database is totally unusable for time series prediction because it's on the longitudinal, on the time axis, totally distorted. And it's nearly impossible to normalize this data on the time scale, because the test scenarios change from week to week, and we distinguish different terrestrial units, towns, and so on in Germany, and they all have totally different test coverage and so on, and it's nearly impossible to normalize this afterwards. So we totally failed to make any reasonable time series prediction of the infection rate to see in the future, like weather forecast. But then we used agent-based simulation combined with partitioned cellular automata for subdomain simulation, and finally applying surrogate modeling to this simulation to get a simulation data-driven model to predict the future of a system aggregate variable observable, that means infection rate. And again, digital twins are used to use mobile crowd sensing to, in this case, not primarily human interaction, but to update by web scraping the database. And here you see the basic concept. We partitioned Germany in terrestrial units, and each terrestrial unit is handled by an agent that controls the partitioned context-aware cellular automata, seen here, with different areas, work, outside, home. But important, we use the public available data, but by performing mobile crowd sensing and web scraping, we update the data in the simulation. And in the simulation, we created a surrogate, or from the simulation data, we created a surrogate model, data-driven machine model. Again, a long short-term memory architecture for the time series prediction here of the infection rate. And in contrast to the real-world prediction that totally fails, here we were able to predict the infection rate 4 weeks ahead. Yeah? And with a high accuracy. So it's still not the real world, but in the simulation world, with the synchronization of real world data, we were able to predict the development of a system aggregate variable by combining agent-based methods with cellular automata and the synchronization with real-world data. Okay, these are the main areas in self-organizing systems: agent-based systems, data-driven models, distributed data-driven models, local prediction, global fusion to get the system aggregates. But if we concern technical systems, we have to consider embedded systems and their constraints. That means transformation and scaling of algorithms and architectures to fit unreliable tiny embedded systems is another important research topic, and it's one of my favorite research topics. So Here you see an example from our DFG research group, an embedded sensor node integrated in the fiber metal laminate structure. And after embedding, you have no direct connectivity to the sensor node, and only you can communicate via RFID with this sensor node. Only have a very small, tiny ARM Cortex M0 with about 8 kilobyte memory, RAM memory. So very tiny embedded system with two issues or two constraints: resources and communication. And so virtualization is another very important topic. After this node is integrated in the plate, you have no chance to reprogram this node. Yeah? You have only very dedicated RFID communication. And so virtualization is a very important topic still, and even in tiny embedded systems. And you will see here different virtualization layers, starting from parallelization, distribution, machines, organization-related topics, processes, communication, peripheral devices, storage, and networks. And agents, of course, are a virtualization methodology, but others are specific virtual machines, up to 4 stack-based processing systems implemented in digital logic directly, and so on. So virtualization is another very important research topic in my field. And of course, algorithmic scaling, that means downscaling and transformation of algorithms for low resource embedded systems with less than 100 mega instructions per second and less than 1 megabyte RAM-ROM resources. And this includes 4 main design principles: decomposition and distribution, already introduced. That means localized sensor data processing and distributed information inference with a hierarchical architecture and distributed architecture. Downscaling, that means reducing the data complexity, data accuracy from floating point to integer arithmetic, for example. Algorithmic complexity, reducing algorithmic complexity. Algorithmic substitution, reducing data-driven models by physical models, for example, and approximation of modeling or models. Model-based approaches, that means feature selection, model fusion, model reduction, model substitution, and finally hardware accelerators on hardware and software basis. That means coprocessor using high-level synthesis, for example, with my Conpro synthesis framework, synthesis of algorithms of software to hardware. Yeah, and this addresses a new topic, TinyML. Even a square millimeter computer provides today enough capabilities to perform machine learning, and that means here the ARM Cortex M0, we can expect about 100 MIPS per square millimeter computation power, 100 kilobit memory per square millimeter, but only 100 microwatt per square millimeter power consumption, and a communication capability of about 100 kilobit per second. So, and even an artificial neural network fits in this very small ARM Cortex M0. Yeah? So TinyML is a very important topic. Okay, to summarize. Complex systems can be composed of simple interacting communicating cells featuring self-start capabilities. Main principles are decomposition and distribution. Self-organizing distributed systems can provide increased scalability, reliability, and resilience in strong, heterogeneous, and harsh environments. That means Internet of Things, Internet of People, material integrated systems. And finally, combining of agent-based methods with machine learning provides a versatile and scalable architecture. Thank you for your attention. This talk gave a relatively compact overview of my research topics within and over the last 10 years. Thank you for your attention.